right, so if I've got, that's for saturated mixture for water, and that works for water in R134. If I've got a liquid, if I do happen to find myself in this compressed liquid phase, then my V value is going to be approximately the V value for saturated liquid at the given temperature. Right? And this approximation is also true for U, H, and S. At least for our purposes, it gets us pretty close. You do have a compressed liquid table for water. If you have a really high pressure, you can see if you can find yourself on that table. But unless your pressure is really high, this approximation works just fine. Go look at the saturated liquid value at the given temperature, and that works just fine for U, H, S, and V. It is an approximation, but it gets us really close. And if it's R134, if I've got compressed liquid R134, this is the only approximation I have in our text, as our text does not have a compressed R134 liquid table. Okay, so anyway, that's water in R134. Let's talk about ideal gases. Okay, so if we talk about ideal gases, then, well, you've got your ideal gas law. PV is equal to RT, or P big V, total volume, is equal to mass times the gas constant times T. Again, this is the universal gas constant divided by the molecular mass. This is specific to the individual gas. We go look these up in table A1, as we've done since very early in the semester. Okay, so if I've got an ideal gas, and if normally what I need to know if I've got an ideal gas is the temperature. If I need to know based on some other properties the temperature, or if I need to know one of these other properties based on the other two. If I know I've got air, or oxygen, or nitrogen, something that I would normally deal with in the gaseous phase, this is a good approximation. It is only an approximation. We've talked about that before. But for our purposes, if I've got air, you're welcome to treat it as an ideal gas always in our class. Moving forward, that may not always be true for you. For us, if you're dealing with air, you can treat it as an ideal gas. And the other thing to remember is a change in internal energy, delta U for an ideal gas, is approximately C sub V T2 minus T1 if you'll get the average C sub V. Don't just pull C sub V at room temperature. Because what this actually is U2 minus U1 is actually equal to the integral from T1 to T2 C sub V dt. And here we're saying, well, let's assume this is reasonably constant at the average temperature, so it comes out of the integral. Then I'm just integrating dt. Well, that just becomes delta t, and here we are. So delta U is approximately C sub V delta t, and also H2, the enthalpy at 2 minus the enthalpy at 1 is equal to the integral from T1 to T2 of C sub P dt. And most of the time we don't worry too much about that integral. We just approximate it as C sub P at the average temperature times the change in temperature. You can actually construct a third order polynomial for ideal gases for C sub P and actually integrate that polynomial within this expression, and that's okay. That's a lot more effort than I'm asking you guys to do here for not a whole lot of precision, in my opinion. So a good C sub P and a good C sub V average value gets you really good approximations for delta U and delta H, respectively. Okay? All right, so that's determining properties for ideal gases with the exception of the entropy. We'll talk about the entropy when we get to the second law here towards the end. Okay? All right, so that's chapter 3 and part of chapter 4. The ideal gas stuff kind of comes up in the specific heat discussion comes up in chapter 4 for us. Also within chapter 4 we talk about well, we could talk about the first law, but before we talk about the first law, let's talk about the first law. Let's just dive right into the first first law of thermodynamics. Now, we talked about the zero law. We talked about the third law. And that's not really part of our objectives. It's just our objectives is just talk about those, but really focus on the first and second law. So let's talk about the first law of thermodynamics. The first law of thermodynamics says the rate at which energy comes into a system minus the rate at which energy goes out of the system is equal to the change in the energy of our system with respect to time. E dot in minus E dot out is equal to dE dt. In minus out. I'm going to write that. In minus out equals change. True of just about any conservation law you're going to encounter. In minus out equals change. First law is no different. Now, if we're dealing with a closed system, okay, so if we're dealing with a closed system, we're probably not as concerned about every little differential change in the energy of the system over every little differential change in time. So what we normally do is we say, well, let's approximate this as the total energy change of the system over a total time period. Now, if I do that, then I say, well, let's say that the change in time multiplied by these rates here, the E dot in minus E dot out, well, if I take time multiplied by rate, I get the total amount. That just becomes E in minus E out. So again, the dot above a variable tells me it's per unit time. So if I multiply per unit time by time, then I just get the total quantity. So the total energy in minus the total energy out is going to equal the total energy change for our system. Okay? Now, so the interactive part here, be ready to pause the video. Tell me, what are the ways that energy can come into or go out of a system? Pause it until you have the answer. There are 3 ways energy can come into or out of the system. Pause it until you know all 3. What are they? Heat, work, and mass. So I can have heat coming into the system, I can do work to the system to add energy to it, and I can also have mass coming into the system. Okay, and then all of those things can go out. There's Q out, there's work out, and then there's mass out. And that's going to equal the change in the energy of my system. Now the types of energy, what are the types of energy? Again, get ready to pause here. What are the types of energy that can change within my system? Go ahead and pause. There are 3. Make sure you know them. What are the types of energy that can change from my system? Well, that's internal energy, and I'm factoring my mass out. I'm assuming my mass is constant. We'll talk about that in a second. So factoring my mass out, I've got to change internal energy. I've got kinetic energy. And I've got potential energy. Now, for a closed and also stationary system, 3 things go away. If it's closed, there's no mass crossing the boundary. That's by definition of a closed system. So the energy of the mass crossing the boundary is 0 because there's no mass crossing the boundary. If it's stationary, that means its speed is not changing and its elevation is not changing. Therefore, its kinetic energy and potential energy are now constant. So for a closed stationary system, I'm not sure what that is. And so for a closed stationary system, well, if I go back here and look at this guy, well, these are going to go away. Right? The masses are going to go away. And this is going to go away, and this is going to go away. So this becomes just delta U, And the only thing I'm left with here is heat and work. Q in plus work in minus Q out minus work out is equal to M delta U. Now, some of you guys watching this video may not actually be in my class. You may not be learning from the textbook we use, that's Changel and Bowles. Maybe you're using an older set of authors, or using more traditional sign convention approach. And so they've probably taught you that Q minus W is equal to U, and that's okay as long as you understand what that means. This is always true. Q minus W is equal to U is only true in the sense that you're forcing a specific sign convention. If I say Q minus W is equal to U, then what I'm saying is well, Q represents Q net in, the difference between Q in and Q out. And if I'm saying minus W, well, that's the net work out, the total work out, being the difference between work out and work in. Right, so or, where, and this is okay for anybody to use. This is fewer terms. I can just say, well, Q minus W is equal to M delta U. That's fine, as long as you understand what you're saying here. For this to work, you're making the assumption that heat in is positive and work out is positive. Our textbook doesn't start out that way. Our textbook says we'll just add the energies in, subtract the energies out, that equals the change. And this fits with all other conservation laws if we start out this way. So this is the reason our textbook starts out that way and just simply says, well, just think about in minus out equals change. I personally have grown to like that a lot more, but this also works. If this is confusing, if you're in my class and this is confusing, don't worry about it. We've mentioned it a few times, but I've made it clear you don't have to necessarily work it this way. It helps if you understand what this means when we get to the second law. We'll see that in just a little bit. But for us, for closed stationary systems, this is our first law. And that's not uncommon that we'll deal with a closed stationary system. Or we may deal with a what we call a steady flow, or again, if you're a guest, maybe you call it a steady state, for steady flow control volumes. So again, the difference between closed systems and control volumes, a control volume is a system where mass crosses the boundary, at least for our purposes in an introductory thermo course. A control volume is just simply kind of an open system, if you will. Mass crosses the boundary. Well, if it's steady flow, that means everything is constant with respect to time. That's what this term steady flow is referring to. Our text calls it steady flow. Some texts will call it equilibrium. Some texts will call it steady state. And these are all referring to the same thing, where ddt goes to 0. So if ddt goes to 0, we're saying this right-hand side change for the system over time goes to 0. And so then we're saying, well, the rate of energy in minus the rate of energy out is equal to 0. Because dE dt goes to 0 if it's steady flow. Now, if that's true, all right, then what else have we got here? Well, again, think about what are the ways that energy can cross the boundary. We've already said the ways that energy can cross the boundary, right? That's heat, so Q dot in. Now I'm putting dots because these are all per unit time. The power input, W dot in, plus the rate of energy for any mass coming into the system. So as I add mass to the system, that mass has its own energy that it's going to add to the system. And then all these quantities could also go out. I could be losing heat at a rate, Q dot out. I could be losing a power output through a turbine or some kind of rotating shaft. I could also have mass leaving the system, E dot mass out. If it's steady flow, that's 0, and that's a stopping place. Loud pop.